Okay, I started the recording. Please note that last Tuesday, for a technical problem, I think I also wrote on YouTube, I didn't have the last hour after the last break. I'm sorry for that, unfortunately. Unfortunately, it's sometimes with the connection, it's a bit of a problem. The connection and the interaction of the many programs that I have open on the PC altogether. So it's basically, I realized that there is an additional risk with respect to the traditional lectures, which is the fact that everything is concentrated in one device. And when I instead I deliver physical lectures, at least the camera is an independent device. So when I start the camera, it's okay. And I mean, even if the PC has some problems, then the camera is anyway working. The camera is very reliable. Instead, here everything is in one device, and there is less reliability with respect to the camera, for instance. And so I have always to make sure that everything is working fine. But anyway, I am getting used. I thank you for your patience, and I know that a couple of lectures are missing from the YouTube videos, but I hope that you can bear with me, and if you have any need, anything that is missing, and you would like to get some details on, please let me know. Okay, now today I want to talk with you about first of all an exercise that I would like to make with you, and it's an exercise that I just developed, and therefore it's also an exercise that requires your cooperation. So I just wanted to propose to you to have a look at it, and we can start with the first part, which is very easy. The second part is something that we need to develop together. I am explaining you just in a second. This exercise is related to computation of mooring forces, something that we didn't analyze in detail. I just, when we had our lecture on the computation of the environmental forcings on moorings, I said I concentrated on computation of the wind forces, forces induced by currents, and I didn't focus on the computation of the mooring forces. I just wrote that the computation is carried out with the traditional techniques of structural mechanics, which basically deal with the composition of forces. Basically, when you compute the mooring forces, you have to make an equilibrium between the environmental forcing, like wind pressure, for instance, against a ship, and the reactions which are given by the mooring lines. So in principle, it's a classical problem, but actually the computation is not easy. It's not easy because it's an hyperstatic or hyperstatic, I don't know how you are used to pronounce it, problem, because usually a ship is a body with 3 degrees of movement. The ship is treated as a rigid body with 3 degrees of movement, but we may have something like 6 up to 10 or more than 10 mooring lines. So there is an excess of bindings with respect to what is strictly needed for fixing a rigid body to the berth, which has a 3 degree of movements. And also the mooring lines are elastic lines, and they, of course, the ropes have elasticity or elastic modulus, and they basically act as springs with an elastic modulus and a spring factor which regulates the increase of length of the ropes of the mooring lines under the forcings. So the problem is a bit complicated, and actually it is often resolved with the simplified procedures, but I just wanted to discuss a little bit the problem with you. I don't think it is really something that we need to learn to perform in detail. The reason is that usually the problem is solved with a software, a software that is able to resolve this hyperstatic problem. On the other hand, I think it is important that we know the basics for the usual reason that when you use a software, you should know the basics. Okay, after this introduction, I suggest that we have a look at the web page. So let me share my screen. As I said, this is an exercise that I put together yesterday, and let me see if okay, you can now see my screen. This is the usual web page of our course, and now you see here an additional link: computation of wind actions on a moored ship, and the computation of mooring forces. So if you click there, you see this exercise, and actually it is the first time that I structure the exercise through web page. In the past, as you know, I put the text of the exercises in PDF, and then I decided that it's better to do it in this way because given that I am now completely basing my lectures on my website, I think this gives more flexibility. Okay, so let's read this exercise. I pass to the bigger page. Just let me remove this. Perfect. Now let's have a look. A ship with a displacement of 3,350 tons. So the first line gives to you the behavior characteristics of the ship. So what is the displacement? Let's have a look at this link. The displacement, you know already it, but I think it's better if you make it clear. The displacement of a ship is its weight based on the amount of water that the hull displaces at varying loads. So it is basically related, the displacement, to the volume of water that is displaced, put aside when the ship is immersed into the water. And the computation, it is based on Archimedes Principle. So basically we know from Archimedes Principle that when a ship is standing into the sea, its weight is equivalent to the weight of the volume of water that is displaced. So when we talk about displacement, basically we mean the ship weight, but actually it is defined as the weight of the volume of water that is displaced by the ship. Okay. So the displacement is 3,350 tons, a waterline length of 117 meters. These terms were all defined in a box that I put here. Just one second, I go back to see the definition of these terms. I think it was in let me see, I think it was here or the previous one. Let me check. Okay, I think yes, this is the box I meant. So here you see the definition for all the terms that I'm talking about. Now I go back to the previous page, but if you open this, it's the lecture on forcing estimation for Harbour design. You find the definition of the waterline length. Probably you don't need to refresh these definitions, but in any case, it's here they are. Also, you can see in the figure below, the length D is the draft. Okay, it's the distance between the lower part of the hull and the waterline. Okay, let me go back now to our exercise page. So the waterline length is 117 meters, the draft is 5 meters, the beam is 12 meters. Actually, we are not using this data, but I just wanted to give to you the full behaviors of the ship. The pivot point, you know, the pivot point is the point around which the ship rotates under the pressure of winds, for instance. The pivot point is located at 55 meters from stern, and the side projected wind area is 950 square meters. So this boat, let me see if I can refresh this page, just 1 second, because the figure is still in the previous photo. Yes, now it's the new picture that I uploaded this morning. So this boat is moored to a berth with 10 mooring lines displaced as in figure 1. Just to give you an idea, usually a boat of this length and this displacement tonnage, it's moored with usually 6 mooring lines in normal conditions, and under extreme conditions they put additional mooring lines, and they can get to a number of 9, 10, 11 or even 12. There are usually several points called bits into the boat where you can fix a mooring line, and then the mooring line usually is fixed to the bollards on the berth. So it's important that we know these terms. I just want to remind you that besides the figure that I showed you before, I have also linked an interesting page with the terminology in another lecture. Let me show you where it is. So let me pass again to the page of our course. I think terminology was here. Port planning and environmental impact. Let me see. Let me see. I need to find it because, okay, terms. Let me see. Or be patient a little bit. No, it's not here. So let me just check here again. Forcing estimation for Harbour design, and just 1 second. Okay, here it is, just above the figure that I showed you before. I put a link to an exhaustive glossary of nautical terms, and this is, if you click, this is definitely interesting. You can see in Wikipedia everything you need in terms of terminology. And for instance, let's look for bollard. You see, here it is a substantial vertical pillar to which lines may be made fast, generally on the quay side rather than the ship. So when it's on the quay side, on the berth side, is called bollard. When the opposite hand of the mooring line is the bit. Let me see if there is the term bit here. Yes. You see bit, a post or pair of posts mounted on the ship bow for fastening ropes or cables. Another interesting terminology when we talk about mooring lines is the, let me see if it is, yeah, it is here, the chock. The chock is a hole or ring attached to the hull to guide a line via that point. So let me just be more detailed, and let's look for a picture. Chock ship. Okay, here it is. Let's click here. You can see an example. Just 1 second. I'm just clicking clicking on the first image that I could find. It's a bit okay. It's always okay. You can see here an image of a chock. So it is an aperture in the body of the ship that guides the mooring line. And usually the mooring line makes an angle on the chock. And it's important to know, when you want to compute the mooring forces, it's important to know the position of the bits, the chock, and the bollard. Okay, now let's close this and go back to our exercise. Okay, so this ship is subjected to an extreme wind velocity of 50 knots. You know, 50 is really very extreme. When we dealt with environmental forces, we said that it's very unusual that you consider wind velocities above 40 knots, because when we exceed usually such wind velocity, then there are emergency procedures that are taken in order to mitigate the forcing on the ship. And for instance, the ship may take on ballast to reduce the windage area, or may decide to unberth in order to better manage the forcing. In any case, it is reasonable. 50 knots in some extreme cases, you may ask it to consider also such wind velocity. But you understand, it's a wind velocity of about 90 kilometers per hour. It means that it's also problematic to stand on your feet when there is such wind velocity. So it's really extreme. And we assume, for simplicity, that the wind direction is perpendicular to the ship's center line. And so let's compute the wind force and the yaw moment, which is the rotational moment around the vertical axis that passes through the pivot point. Now, and then there is a second question suggested. Read the procedure here below for computing mooring forces, then make a trial computation by assigning, and here there is a spelling, just one second, I take note. There is a G that is missing. By assigning values to the input variable we're missing. And for instance, you need to know the coordinates of the bits, chock, and bollards, and the angles of the mooring lines. I'm taking notes of the spelling errors. Just one second. They are not really important, but given that I see them, I would like to then afterwards to correct. There is an assumption which is that the mooring lines are horizontal, which it's not the case usually. Usually the mooring lines are going upward from the berth to the ship. The angle really is not very significant usually, but still they are in most of the cases, especially for big ships, they are moving upward. But if you just assume that they are horizontal, you simplify the problem a lot, and the assumption can be easily removed. So let's assuming that they are horizontal, and let's assume that CW is 1.3. We will see what is CW. We already studied it. So there is a first part which is easy. The first question: compute the wind force and yaw moment. This is easy. Now let's open R, because I suggest that we make the computation in R. I would like to make an attempt to create an R program that computes the forcing, the environmental forcing, and the mooring forcings by just giving the input data. And this could be a nice goal for us. as I said, the second question is still to be resolved. So let's start with the first one. The first one is easy. It is something that we could more easily carry out in Excel rather than R, but given that we have to improve our knowledge of the software, let's open RStudio. If you have any doubt, any question, please stop me. Just let me show the chat on the other screen so I can have a look at your questions, if any. Okay, now on the other screen I have the chat. Yes, okay, no questions so far. So let me open RStudio. Here it is, and let me clean everything if needed. Just let me see if, okay, yeah, there is, let me change the directory, set working directory, I change it. Okay, and then let me clean the history. Just 1 second, connections, okay, history. Okay. Okay, and then let me save this file with another name. Okay, no. And let me save it like mooring forces.r. Okay, this is our script. And then let me clear the console. Good. And then I just would like to clear the history. I don't remember how should I do. And let me see. Okay, I think I just have to select everything and then click on the red cross. Yes. Okay. It's a long history, so give me some time. Let me see if I can select all. Yeah. No, it was not selected. Just 1 second. Okay. Okay, now I am fine. Perfect. Everything is clear. Okay, now let's go to the script file here and let's start, and let me put a comment with the title computation of environmental forcing and mooring forces. Give me 1 second, students, that I need to reply to this call. Just 1 second. Sì. Sì. Ah, perfetto. Non ci sono problemi. Grazie, grazie a te. Ciao, ciao. I'm sorry, I need to keep the phone open because I need to stay in touch with the university all the time, so be patient. So, computation of environmental forcing and mooring lines, and a second line for a berthed ship. Good. Okay, now let's fix the data here. So I would create a function, and let's call the function something like moorings equal function, and then I have to put the arguments of the function. So let's start with a simplified version with all the data that we need. And one important thing, students, if there is something that you don't understand of what I am doing, just let me know, okay? Stop me. I assume that you are still seeing the screen, and unfortunately with the phone call I cannot check on the phone anymore. So if there is any problem with you, just let me know, okay? So what I am creating now is an R function, which in my view should allow me, once that I give the input data, to compute on the one hand the environmental forcings, so the yaw moment and the wind pressure and the wind force, and later on, subsequently, the mooring forces. Okay, so let's give as arguments of the function the wind velocity, so let's call it VW. We don't give default values, or let's give default values in order to learn how to do it, and in order also to not to have to put the input data every time that we run the function. So given that the function now is conceived for this specific exercise, let's give default values with the data of this exercise. In the future, if this function will be applied to other cases, we can remove the defaults, but now we can do them, we can give them. So the wind velocity is 92.6, if I will remember. Now I go to the web page to see the data, because I don't want to make mistakes. Oh, here I am, just 1 second. Okay. So let me see what is, yeah, 92.6 is the wind velocity. Good. Now, for sure, I need the side area. So the side area is 950 square meters. So let me go back to here, and I can call it side area in order just to not to make confusion. Okay, and then another indication that I need is the angle alpha is 90 degrees. Alpha is the angle between the wind direction and the ship center line. It's 90 degrees. And now let's see what other data we need. So I don't think we need the length of the waterline now. We don't need the displacement. Draft and beam are not needed. Maybe the pivot point, the location of the pivot point, but I don't think we need it now. So let's, I think we are done. CV is the coefficient. We will see what is 1.3. Okay. And then we can open a curly bracket. In order to make the curly bracket in my keyboard, I pushed Alt-GR, and by keeping pressed Alt-GR, I also press the key of the number 7 in the upper part of the keyboard. And this basically opens and closes the curly bracket. So let me do it again. Alt-GR plus 7. And so let me delete the closing curly bracket. I need to keep it open. Okay. Now let's save it. Let's click on the disk. And then let's go back to the web page where there is a proposed solution. Okay, so let's go down. Solution, computation of the wind force. From the equation 1 in the web page of computation of environmental forces, which is linked here, we get from that web page that we have to use this relationship. This is general for any value of wind direction. So in this case, the wind direction, this is a simplified case. In this case, the wind direction, as we know, it's perpendicular to the ship center line. And therefore, alpha is 90 degrees, and the sin of alpha is 1. And the cos of alpha is 0. So this formula, this element here doesn't appear. And this is why also in the exercise we were given no indication of the transverse area exposed to wind, BW. We didn't get any indication on that because given that BW is multiplied by 0, we don't need to know it. So by adopting CV equal 1.3 and side area 950 and phi 90 degrees, and then we have this value for the density of air, which is also given in the web page linked above, and then we take the given wind velocity, and then we take in meters per second, the wind velocity is 2572, but we will compute it. And then taking the gravity at 9.81, we obtain this relationship here. So let's compute it. First of all, alpha 90 is not good. We should write alpha is pi half. I don't remember, I look in the console. If pi is, yes, pi is the symbol that R uses for pi to indicate pi. And 90 degrees, as you know, is pi half. And we have to use the angle not in degrees, but in pi's, because in radians, sorry, because this is the usual way R deals with angles. Okay, now the wind force, let me go back to the web page. I need to jump back and forth because I want to use the same symbols. So be patient if I jump back and forth a little bit. Here it's PW, so let me call it PW is equal to, okay, let's write CW times the side area times, let me go back because I want to make sure, okay, sin of alpha squared, if I will remember, let me see, yes, and then air density times 0.1225, 0.01225, and then times, now the wind velocity. Wind velocity is given in kilometers per hour. So we we need to convert it to meters per second. So let's write Vm divided by 3.6. This is the conversion factor. Okay. Now square. Just 1 second. So I need to square with the parentheses. Square divided by 2 divided by 9.81. I think we should be done. Okay, very good. So this is PW. Now let's make a check. At this stage, we can, I suggest that we run the function to check whether the result is coherent with what is presented on the web page. So how to run the function? First of all, we have to instruct the function to give back the value of PW. So return PW. And then we need to close the curly bracket, and it's Alt-GR plus 0. And I think at this stage we can run it. In order to run it, I have to source the function. Okay, I clicked on, I'm sorry that you don't see the mouse, but now you see the black rectangle. I clicked on source. And you see on the console, it appears the confirmation that the program, the function was sourced. I can do it again. You see the black rectangle where I am clicking, source. And when I sourced, I didn't find any error, so I hope it is fine. And at this stage, I can just type the name of the function, and there are the default values, and then it should work. Okay, there is an error. Let's see the error. Okay, the wind velocity. I made a mistake here. It's not VM, but it's VW. Okay, I corrected it. Let me save it, source it, and then let's try again to run the function. I go to the console, and in order to run the function, now I use arrow up to get it again. It's 510. Let's see whether it is coherent with what I reported in the web page. It seems not. So let me see what is